The transistor is the electrical component without which computers, smartphones, smart TVs, and virtually any modern technological device couldn't exist. And this is seriously true. The transistor, or better yet, thousands, millions, or even billions of transistors, makes up the core of CPUs, essentially the brain of every electronic device. In this video, Bob, who is passionate about electronics and technology, wants to understand how a seemingly insignificant component can carry out the complex operations required in modern technology. Bob takes a transistor and wants to study it to understand how it works. A transistor is graphically represented in electronic engineering with a symbol in which the three characteristic terminals that distinguish it are clearly highlighted. The three terminals are called base, collector, emitter. Bob creates a simple circuit in which he inserts the transistor. Bob powers the circuit with an electric current source and wants to understand, thanks to the presence of an LED light, how the current flows and therefore how the transistor works. Bob sent an electrical signal to the base terminal and noticed that the LED light turned on. This means that the current coming from the collector terminal flows through the emitter terminal and reaches the LED, which consequently lights up. I represent the presence of an electrical signal at the input terminal with the symbol 1. As soon as Bob stops providing the electrical signal to the base terminal, he notices that the LED light turns off. This means that the electric current no longer reaches the emitter. For graphical convenience, I represent the absence of an electrical signal at the base terminal with a 0. To simplify, Bob realizes that the transistor behaves like a switch, whose on or off state is controlled by the presence of electrical signals at the base terminal. So, he takes notes on what happened. When no electrical signal is sent to the base terminal, so input is 0, the result is LED light off, meaning output is 0. When an electrical signal is sent to the base terminal, so input is 1, the result is LED light on, meaning output is 1. At this point, Bob modifies the circuit structure by placing the LED light in parallel with the transistor. Bob powers the circuit and takes note once again. When the input to the base terminal is 0, the LED is on. Instead, when Bob inputs a 1, what happens is that the electric current leaves the branch of the circuit where the LED is located and flows through the branch with the transistor as it finds less electrical resistance there. As a result, the LED turns off. Bob finds this behavior quite interesting. In fact, it's so interesting that the evolution of this simple circuit is widely used in electronic engineering. This type of circuit has its own dedicated circuit symbol, and in logic analysis, it's called a NOT gate. Bob continues with his transistor experiments and further modifies the circuit, making it more complex. He inserts two transistors in series and powers the circuit. When Bob inputs 0 to both the base terminals, the LED remains off. Bob takes note, the output is 0. Bob inputs a 1 only to the first of the two transistors and the LED remains off, so the output is still 0. Bob gets the same result by inputting a 1 only to the second transistor. The LED light remains off. At this point, Bob inputs a 1 to both terminals and the LED finally turns on. The output is 1. The result obtained with this circuit is significant. The output is 1 only when both inputs are 1. This circuit in electronic engineering is known as an AND gate and is represented by a dedicated symbol. Bob modifies the circuit again by placing the two transistors in parallel and powers it on. Bob takes note, by not inputting electrical signals to the base terminals of both transistors, meaning an input of 0, the LED does not turn on, so the output is 0. Bob now inserts an input of 1 only to one of the two transistors. The LED turns on. Bob then changes the setup and inputs a 1 only to the second transistor and sees the LED light up again. The output is once again 1. Bob inputs a 1 to both the base terminals and the output remains 1. This result is also significant. The output is 1 when at least one of the inputs is 1. This circuit in electronic engineering is known as an OR gate and is represented by a dedicated symbol. Summarizing, Bob has understood that transistors are very simple electronic components, but when placed in appropriately configured electrical circuits, they can be used to generate more complex results. So far, Bob has managed to create the logical elements not and or, but when he connects these circuits together, he is able to achieve even more diverse behaviors. Bob is therefore able to create the other logical components at the core of modern electronics: XOR, NAND, NOR, XNOR. Now that Bob understands the theoretical foundation built with transistors, he wants to use this knowledge to perform practical operations. Bob decides to carry out a simple task. He wants to add two numbers and he chooses basic values, 0 and 1. So he calculates, so 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1 should result in the value 2, but the value 2 doesn't exist in electrical circuits because, as we've seen, electronic components can only handle two values, 0 and 1. Therefore, to calculate the sum, Bob switches from the decimal number system we're used to the binary system, which is native to computers. 1 plus 1 equals 1 and 0. Bob moves these simple operations into a table format and notices that for two input values, there are two corresponding output values. Focusing on the first output, he sees that it behaves just like a logical AND, while the second output corresponds to a logical XOR. Now everything is clear to Bob. To perform his mathematical operation, all he needs to do is build an electrical circuit that includes the two logic components he identified in his little table. Exactly. By inputting 0 into the logic components, the result he gets is 0, which is exactly what he needs. By inputting a 1 only into the first of the two terminals, Bob once again gets the expected result. The XOR logic component outputs a 1, while the AND logic component returns a 0. He gets the expected result even when the electrical input signals to the logic components are swapped. Finally, the result is still correct when Bob inputs 1 into both logic components. The XOR returns 0, while the AND component, as expected, returns 1. This circuit is called a half adder because it can add simple numbers that are represented using only two symbols, 0 and 1, also known as bits. Bob connects several half adders together. In this way, he manages to add numbers represented by 8 bits, or more precisely 1 byte. This circuit in electronic engineering is called an 8-bit adder. Bob is happy. By using simple transistors, he was able to build an electrical circuit that processes data. Depending on how the input signals are provided, the circuit returns the expected output. Bob uses the same basic logic components, and by following the same procedural approach, he also creates other electrical circuits needed for mathematical operations. He creates an 8-bit subtractor, which is necessary for subtracting two 8-bit binary numbers, and 8-bit incrementer used as a counter. But now Bob has a problem. He has created several circuits capable of performing mathematical operations, but which one should be selected to carry out a specific task? How can he activate one circuit while keeping the others off? Bob draws on his experience with basic logic components and builds a multiplexer. The multiplexer is an electrical circuit with characteristics very similar to those he has already created. A specific output corresponds to a particular set of input signals. In this case, the output is used to power one of the mathematical processing circuits. The electrical circuits dedicated to mathematical operations, together with the multiplexer, form the essential elements of the ALU, or arithmetic logic unit, the first of the three fundamental parts that make up the CPU. The other two essential parts are the registers. These are small-size memory units directly integrated into the CPU, providing instant access to data for the other CPU components. They store temporary variables resulting from data processing. The CU, or control unit. Its role is to receive the inputs coming from the instructions of the program the computer is executing at that moment and decode them into simple instructions that can be executed or managed by the other components of the CPU. To summarize, the ALU, CU, and registers are the foundational elements of the CPU's functionality. It is essential that the new set of input signals is received and processed by all components at exactly the same moment. Otherwise, the logic components would return transient and likely incorrect results, which would lead to a malfunction of the entire system. Bob finally connects a clock to his CPU. The clock circuit plays a fundamental role. It must ensure that all transistors and other electrical components always operate in perfect coordination with one another. The clock measures its speed in hertz. A clock running at 1 hertz means having a circuit capable of changing the inputs to the transistors once every second. Having a 2 hertz clock means having a circuit capable of changing the inputs to the transistors twice in 1 second. A 4 hertz clock means having a circuit capable of changing the inputs 4 times in 1 second, and so on. Today, CPUs operate in gigahertz, meaning the inputs to the transistors change billions of times per second. The higher this value, the faster the CPU is at performing computations.